So this will be the case of where we return to x and p operators and non-denumerable bases. Non-denumerable basis. So we're going to try to do x and p. Now, this is the classic of Dirac notation. It's probably, as I said, the place where everybody likes to use Dirac notation. And the reason it's efficient is because it prevents you from confusing two things. So what was the, I've written in the notes that we have all these v's that belong to the vector space, and then we put this, and we still say it belongs to the vector space. And this is just a decoration that doesn't do much. And we can play with this. Now, in the non-denumerable basis, the catch and the possible confusion is that the label is not quite a vector in the vector space. So that is the reason why the notation is helpful, because it helps you and helps you distinguish two things that you could confuse. So here we go. We're going to talk about coordinate x and the x operator and the states. Well, this is a state space. So what kind of states do we have here? Well, we've talked about wave functions, that we could give the value of the wave function at different places. We're going to go for a more intrinsic definition. We're going to try to introduce position states. And position states will be called this, x. Now, what is the meaning of this position state? We should think of this intuitively as a particle at x. Now, here is how you can go wrong with this thing. If you stop thinking for a second. What is then AX? Is it AX? A being a number. Is it the same thing? No, not at all. This is a particle at the coordinate AX. And this is a particle at x with some different amplitude. Very different. So this is not true. Typical mistake. This is not minus x. That's totally different. So there's no such thing as this either. Linear. It doesn't mean anything. And the reason is that these things are not our vectors. Our vector is this whole thing that says a particle at x. Maybe to make a clearer impression, imagine you're in 3 dimensions and you have an x vector. So then you have the ket this. This is the ket particle at x. X is now a vector, but it's a 3-dimensional vector. This is a vector, but it's a vector in an infinite dimensional space, because the particle can be anywhere. So this is a vector in quantum mechanics. This is a complex vector space. This is a real vector space, and it's the label here. So again, minus x is not minus x vector. It's not the vector. The addition of the bra has moved you from vectors that you're familiar with to states that are a little more abstract. So the reason this notation is quite good is because this is a number, but this is a coordinate, and this is a vector already. So these are going to be our basis states, and they're non-denumerable basis states. And here you can have that all x must belong to the real numbers because we have particles in a line, while this thing can be changed by real numbers. The states can be multiplied by complex numbers because we're doing quantum mechanics. So if you want to define a vector space, now this is all infinite dimensional. It's a little worse in the sense that the basis is non-denumerable. If I use this basis, I cannot make a list of all the basis vectors. So for the inner product, we will take the following. We will take x with y to be delta of x minus y. That will be our inner product, and it has all the properties of the inner product that we may want. And what else? Well, at this moment, we can try to, this is physically sensible, let me say, because if you have a particle at one point and a particle at another point, the amplitude that this particle at one point is at this other point is 0. And these states are not normalizable. They correspond to a particle at a point. So once you try to normalize them, you get infinity, and you can't do much. But what you can do here is state more of the properties and learn how to manipulate this. So remember, we had 1 was the sum of all EI, EI. The unit operator was that. Well, let's try to write a similar one. The unit operator will be the sum over all x's. And you could say, well, looks reasonable, but maybe there's a 1/2 in here or some factor. Well, no factor is needed. You can check that you've defined this thing properly. So let me do it. So act on this so-called resolution of the identity with the vector y. So 1 on y is equal to y. And now let's act on the right. X, x, y. This is delta of x minus y. And then when you integrate, you get y. So we're fine. So this looks a little too abstract, but it's not abstract if you now introduce wave functions. So let's do wave functions. So you have a particle, a state of a particle, psi. Time would be irrelevant, so I will put just this psi like that without the bottom line. And let's look at it. Oh, I want to say one more thing. The x operator acts on the x states to give x, x. So these are eigenstates of the x operator. We declare them to be eigenstates of the x operator with eigenvalue x. That's their physical interpretation. I probably should have said that before. Now, if we have a psi as a state or a vector, how do we get the wave function? Well, in this language, the wave function, which we call psi of x, is defined to be the overlap of x with psi. And that makes sense, because this overlap is a function of this label here, where the particle is, and therefore the result is a complex number that is dependent on x. So this belongs to the complex numbers because inner products can have complex numbers. Now, I didn't put any complex number here, but when you form states, you can superpose states with complex numbers. So this psi of x will come out this way. And now you can, now that you're armed with that, you can even think of this in a nicer way. The state psi is equal to 1 times psi, and then use this formula. So this is integral dx x psi. And again, the bracket notation is quite nice because the bra already meets the ket. This is a number, and this is dx x psi of x. This equation has a nice interpretation. It says that the state is a superposition of the basis states, the position states, and the component of your original state along the basis state x is precisely the value of the wave function at x. So the wave function at x is giving you the weight of the state x as it enters into the sum.